Welcome to this explainer, where today we're diving into the body's incredible hidden electrical network, that lightning-fast system that turns a thought into an action. Let's get right into it.
Really think about that for a second. You decide you want to pick up your coffee cup, and boom, your hand just does it. How on earth does that message travel from your brain all the way to your fingertips? It feels like magic, but I promise you, it's pure, fascinating electricity. Well, the answer lies in our body's very own living electrical wires. We have these amazing, specialized tissues designed for one purpose, carrying these high-speed messages.
And the star of our show today is something called excitable tissue. It's the perfect name, really, because when this tissue gets a stimulus, any kind of signal, it literally gets excited and fires off an electrical impulse.
And this is a really big deal. You see, on one hand, you have excitable tissues like our nerves and muscles. They carry a high electrical charge right on their surface, just waiting for the signal to go. But on the other hand, you have non-excitable tissues, like connective tissue, which have a much lower charge. They're just not built for this kind of rapid-fire communication.
Okay, so how do these cells get so charged up in the first place? The best way to think about it is that every single nerve cell is like a tiny biological battery, fully charged and just waiting for the signal to release its energy.
The whole secret is in the cell membrane. It acts like a gatekeeper, or a barrier, that separates charged particles called ions. By carefully keeping most of the positive charges on the outside and negative charges on the inside, it builds up an electrical potential, exactly like the positive and negative ends of a battery you'd buy at the store. So how does it build this charge? Well, it starts with sodium ions. The cell works incredibly hard, like a little pump, to push sodium out, making the concentration a whopping 10 times higher outside the cell than inside.
But if you think that's a big difference, check this out. With potassium ions, it's even more extreme. The cell actively pulls potassium in, making it a staggering 30 times more concentrated on the inside of the cell.
So here's the full picture. The cell is this master organizer, right? It shoves sodium and chloride ions outside, while hoarding all the potassium ions for itself on the inside. This separation creates this incredible tension, a powerful gradient that's both chemical and electrical. It's a battery that is just primed and ready to go.
And this charged-up, ready-to-fire state has a scientific name. It's called the resting membrane potential. You see, some of those positive potassium ions are always kind of slowly leaking out, which means the inside of the cell ends up with a stable negative charge. It's resting, but it's absolutely ready for action.
So, the battery's all charged up. Now for the fun part. What happens when this battery gets the signal to discharge its power? This is where the magic happens. This is the action in what we call an action potential.
The whole process is this breathtakingly fast four-step electrical dance. First, there's depolarization, then a quick overshoot, followed by repolarization, and a final brief hyperpolarization before it all resets. Let's break that down.
Okay, it all starts with a trigger. These special little pores, or gates, for sodium suddenly burst open. And because of that massive 10-to-1 concentration difference we talked about, positive sodium ions don't just trickle in, they flood into the cell, instantly starting to cancel out that negative charge inside. This flood of ions is so fast and so powerful that the cell's internal charge doesn't just get back to zero. For a split second, it completely blows past zero and actually overshoots, making the inside of the cell positively charged. The battery has just completely flipped its polarity. The cell immediately kicks into gear to fix this. The sodium pores slam shut, and now a whole different set of doors, the potassium pores, swing wide open. And remember all that potassium packed inside? It now rushes out of the cell, carrying its positive charge with it and dragging the cell's interior back down towards negative.
You know, in its big hurry to reset, the cell sometimes overdoes it a little bit. So much positive potassium leaves that the inside becomes even more negative than its normal resting state. This brief little dip is called hyperpolarization. Think of it like a final shutter before everything stabilizes.
So after that whole wild ride is over, a special protein pump called ATPase gets to work. You can think of it as the cell's own personal battery charger. It works tirelessly, using energy to pump sodium back out and pull potassium back in, restoring everything to its original state so the nerve is ready to fire all over again.
Now, you would probably think that a stronger stimulus, say a harder poke, would create a bigger electrical spike, right? Well, that sounds logical, but the body is governed by a much simpler and honestly a more profound rule. It seems like it should, doesn't it? A light touch creates a small signal, and a hard poke creates a huge one. But that is not at all how our nervous system works.
This is the all or none law. It means exactly what it sounds like. There will be a full 100% response, or there will be no response at all. It's like a light switch. The signal is either completely on or completely off. There is no dimmer.
Here's how that works. For a nerve to fire, the stimulus has to be strong enough to cross a minimum threshold. If it's too weak, absolutely nothing happens. But the moment it crosses that line, it unleashes the exact same full-sized action potential every single time. A stronger stimulus does not create a bigger signal. So, we've gone from the big picture of moving your hand all the way down to a tiny, microscopic event inside a single cell. Why does this tiny little spark matter so much?
Well, let's put it all together. Your nerve cells act like tiny rechargeable batteries. When they get a signal, they fire off a rapid, all-or-nothing electrical spike called an action potential. And it's this fundamental process, this tiny spark repeating millions and millions of times every second, that literally powers every single thought, feeling, and movement you will ever experience.
And that leaves us with one last really fascinating question to think about. If every single nerve impulse is identical, if it's the same size and strength every time because of the all or none law, how on earth does your brain know the difference between a gentle grease on your skin and the sharp sting of a paper cut? Something to chew on. Thanks for watching.